Let me introduce the topic of my presentation. It's about the impact of socioeconomic status on academic ability, academic performance of high school students. And in this study, I'm using machine learning. So the first part of my presentation will be explaining difference between traditional methods of the econometric analysis and how much it is different, and how much machine learning is different from the traditional way of doing analysis. So let me move first of all to the background of this topic. First of all, there is huge amount of literature about the effect of socioeconomic status, SES, on academic ability, because this is a very important topic for society, because if there is important effect, so that rich, for example, rich parents can make investment in the education of the children, then in consequence, children can perform better in exams, and then children can secure a better place in universities, and then after getting better education, they can likely to get better jobs. And so across generations, the rich parents will lead to even richer children. So there will be huge further increase into intergenerational inequality. Most of the studies that looked at the academic activity used very traditional methods such as regression analysis, but in recent years, more papers are attempting to try a different approach, such as machine learning. And by one estimate that I citing here from 2020, there was huge increase in the papers which use this machine learning, and most of this 90% actually were published only since 2013 to 2019. So it's very dynamic field with rapidly increasing number of new contributions. Let me explain here the difference machine learning and the traditional analysis. It's very schematic because when I prepared my slides, I had in mind just also general audience, but I think it's quite evident. The difference should be very evident, very clear cut. In the traditional data analysis, it's on the left side. We start with theory, and then based on the theory, we formulate hypotheses, and then we collect data, then run based on our theory and then and our hypothesis, we estimate model, and the focus in the parameters of our model. If the parameter is statistically significant, we are happy, and there is evidence for the initial theory. If result is not statistically significant, then probably something should be done. We may revise our estimated model. So this is the typical way how we do data analysis. In machine learning, the sequence is completely different. First of all, there is no initial model to speak about. We start with data, and without specifying any initial model, we try to look at different patterns in the data, and the goal is to find the best model with the smallest prediction residual. So whereas in the conventional analysis, the focus on parameters, in machine learning, the focus is on the predictive ability of estimated model. And then after we find this, try different patterns, find the best one with the smallest prediction residual, Then, based on this identified pattern, we can formulate hypotheses and probably also modify theory. So the sequence starts not with theory from the data, and the theory is not the beginning, but the goal of machine learning with the initial extensive search in the data. So as I said before, what are the major features of machine learning in addition to this sequence? First of all, as I said before, there is no initial model that we specify. We just provide the list of explanatory variables. They are called machine learning, they are called features. And then machine learning algorithm is trying different combinations of these explanatory variables, and then pick up the best combination of explanatory variables. So we may, for example, may start with 100 explanatory variables, or say 50, but the eventual model with the best predictive ability may include something like 10 or 15 variables, and then the rest are maybe completely ignored. And this is done completely endogenously without any initial specification what kind of model we want to estimate. Also, machine learning is a bit similar to non-parametric econometrics, but there is one big difference. In non-parametric regression, the pattern that we estimate is also not specified. But non-parametric models usually assume that there is a smooth transition across the possibly nonlinear effect. Whereas in machine learning, there is no assumption of smooth change. The effect can be abrupt, very sharp. So it's much more flexible compared with non-parametric econometric models. And also the level of interaction in models could be very high. For example, if we estimate traditional models, usually the highest level of interaction may be up to 2. For example, we may look at subdivide children into girls and boys, and then look, in addition to this intergeneration, these gender differences, what is the interaction, for example, based on social economic status or some other variable. But machine learning, the order of interaction could be as high as we want. Level of interaction, say 5, is very easy to specify. So they can explain very complicated patterns. So if you look at the traditional model, then this is the linear regression model, where Y is, for example, the academic ability result of language test. And then explanatory variables can be gender, then how much student is studying, and also some variables related to household, such as social economic status, etc. And we are interested in this beta 1, beta 2, beta 3, whether they're significant or not. And the important difference here is, so the focus on the parameters, because model is very simple. We just specify it as including variables that we can think about. And the structure of the model, as I wrote at the bottom, is specified by human. For machine learning, we just provide as the list of potential explanatory variables. And then the final model, as I said before, will include only some of them. And very often the most very common algorithm is, for example, a regression tree. Here it's KKG. And we pick up, the machine learning algorithm picks up the variables with the highest explanatory variable, but the structure of model is the final estimated model is extremely complicated. I'll show you later to give you an actual example. It's completely impossible to imagine the complete picture of this model, but this model has excellent predictive ability. So for machine learning, as long as model predicts well, we don't care whether we understand it or not, whether it's comprehensible or not. There are different tools to explain the machine learning models, but the goal is not to look at particular parameter, but at prediction ability. And as long as model is very good in predicting why, then it could be as complicated as possible. And the more important thing is that computer determines the structure of the final model after looking at the data that we start with. Okay, so here I just give you example of the popular machine learning model. It's called regression tree. We start with the initial data set. You can see there are squares and there are circles. So in regression trees, we just divide data by our explanatory variable into two groups. Let's say we have data for academic ability, and our explanatory variables are we have just two explanatory variables. First one is gender. And the second one is social, let's say, income, which varies from, let's say, 1 million yen to, is it okay? Yeah, 1 million yen to 10 million yen. So the actual the data for income is 1 million, 2 million, 3 million, 4 million, and all the way to 10 million. So in machine learning algorithm, we try different data partitions. First one would be by the first explanatory variable gender. So we partition data, because this is data for students, into boys and girls. Next, we try other possible partitions because we have other variable income, which varies between 1 million and 10 million. So the first partition would be 1 million goes to the left, and then 2 million, from 2 million to 10 million goes to the right. Then second partition of income would be 1 million, 2 million to the left, 3, 4, 5, 10 million to the right. And we try all the way until the final partition from 1 to 9 to the left, and then 10 million to the right. We tried these different partitions, and then actually we're using dummy variables to differentiate these two groups and look at the partition which provides the smallest prediction residual, or it can be, we can look from a different angle, how good is predictive ability performance of our model. So because this is data for, let's say this is data for mathematics, I expect that gender differences maybe very large. So that probably the first partition, the most with the highest predictive ability or smallest prediction residuals would be by gender. So here, let's say girls are to the left and boys to the right. Then after we identified the best partition at first stage, we proceed to the second stage. When inside the girls, we try different partitions by income. The first partition, second, fourth, and all the way to the final partition. Let's say for girls, the best partition by income was 1 million, 2 million, 3 million to the left, and then 4, 5, 6, 7, 8, 9, 10 to the right. And let's say for boys, it is from 1 million to 5 million to the left, and then from 6 million to 10 million to the right. This creates a regression tree. Creates a regression tree. Most important thing is that the structure of this regression tree, the variables that comes at the beginning with the highest predictability, is determined by the data. So that we don't need to specify initial model. Everything is decided by the data. This is a very simple example, and the machine learning models are much more complicated, but basically many of them are basically combine a lot of regression trees. Number of regression trees could be 500, 1,000. I'll show you result shortly. So the initial model is the based on partition, data partition in regression trees. But the final regression machine learning model may be include a lot of such models, up to 1,000, maybe 10,000. It's really very simple to calculate really very complicated models. Now I here want to illustrate the feature, the ability of machine learning to model very complicated and abrupt changes. This is the result. Y-axis is the result of academic test. Okay. And then average is 500, standard error is 100, and there are two lines. The first line is the straight line estimated by regression model, linear regression model, OLS, and the blue line is derived from machine learning algorithm, and the model looks at the effect at the class atmosphere, how well-behaved students are. If we go 0 means a standard level, and then to the left of 0 means well-behaved students, and to the right of 0 means badly behaved students. So you can see that the effect of lack of discipline reduces the academic performance results of tests, but the effect is highly nonlinear. For example, once we move from standard class atmosphere discipline from 0, then there is a rapid drop between 0 and 1. But once the discipline is not good, beyond some level, beyond 1, the result is really on academic performance no longer evident. So there is at the extreme, the effect basically disappears. But once we move slightly to the away from the center, then there are relatively sharp nonlinearities. Okay, let me also continue explain another features of machine learning. When we analyze data in traditional way, then we use data both for estimation and for evaluation. We just run regression on the whole data set, and we are happy with this. In machine learning, data partition into the training and testing data set. And the usual training data set is about 70–80% of the data. And we use this training data set to find the best model with the smallest prediction residual. Or root mean squared error. But we can calculate. But after we calculate the root mean average prediction residual on the training data set, we haven't finished yet, because the final evaluation is done on the test data set, the remaining 20–30%, and only if the model performs very well on the part of data which was not used for model search, then the model is judged as good one. It's something like how we are studying in universities. When we are taking, for example, some short test or taking homework to learn a new topic. But then the final evaluation is done by the final exam. In traditional approach, final exam questions would be the same as the questions from the short test, homeworks. Obviously, it's very easy to pass this kind of hurdle. But in machine learning, the final exam is similar to the previously used testing, but it's differently previously unseen part of data. What kind of algorithm are we going to use? First one is the conventional orderly squares, and then comes the algorithms which are machine learning algorithm. The first one is elastic net. In elastic net, we combine two kinds of linear regression. The first one is ridge regression, and the second one is lasso regression. And it's very popular in machine learning textbooks, but this model algorithm has one big drawback, that the effect is still linear. For example, in lasso regression, we can endogenously select the most important explanatory variables. So as I said before, we may start with say 50 explanatory variables, apply lasso, and then lasso picks up only a part of these explanatory variables. But even after selecting the most important variables, the effect still remains linear. So this is that's why this is maybe a serious disadvantage of this algorithm. Random forest is algorithm that was suggested in about 18 years ago. It belongs to ensemble machine learning algorithm, where a large number of regression trees are combined, and the final parameters are the averages of initial regression trees. So the number of regression trees could be 500, 1,000, and the final machine learning parameters in random forest is the average across a large number of regression trees. Gradient boosting machine is another ensemble algorithm, but instead of the finding average across a large number of regression trees, this algorithm tries to improve on focuses on prediction residual. So we start from the at first stage, we estimate modeled by typical regression tree, and then calculate residuals. Then these residuals serve as become the object of our Y at the second stage. So we try to reduce residuals on the second stage, third stage, and can repeat it over many times, 100 times, 500 times. And then the results of these separate steps, attempts to explain away prediction residual, are combined, or basically averaged in a final parameter. And finally, extreme gradient boosting is the very recent algorithm. It was suggested about, I think, 2017. But it's already became extremely popular, and if you in machine learning, there are competitions across practitioners who gets the best model with a given data set, and usually gradient extreme XGB boost is the best algorithm to use. So now I move to one complication. So far, I was talking about good or advantages of machine learning, but there are also some complications in real analysis. The major complication is hyperparameter. In the regression model, because we are learning from the data, the speed of learning, how much our final results get updated, and how complicated our model. Are we going to use 500 regression trees, or are we going to use 1,000 regression trees? There is no theory. Basically, we try combinations of different models, and the structure of this model is controlled by hyperparameters. In the next model, I show you hyperparameters of the XGB boost. And you can basically I try different combinations, and the one which the combination which I found the best one with the smallest prediction residuals are in yellow. Usually there are 36 combinations. I'm sorry. On my computer with 36 cores, it's very easy to calculate this in parallel. Basically, to split computation job across different processors, it usually takes about 30 minutes of processing time. So the first hyperparameter of XGB boost is the number of trees. I tried 100, 300, 500. Then learning rate, how much the contribution of the next regression tree affects the previous parameters. Usually learning rate is set at small number. Here ranges between 0.01 to 0.2. And the best one was 0.05. Then interaction depth is this interaction effect. I tried the basic case with just one interaction until to 9 interactions, and the medium interaction was found the best one. And so overall there are 3 multiplied by 6 multiplied by 5, so and so on. Basically 660,000 combination of parameters, and it took me, as I said, about 30 minutes of computing time to try different machine learning models and pick up the best one which are shown in yellow color. Now, after I explained the machine learning, let me explain the data set that I'm going to analyze. It comes from PISA dataset. PISA started from 2000, but I use data from 2003 until the latest, around 2018. In PISA, there are 3 subjects: the mathematics, science, and also reading. And there is rotation across these major subjects. So every 9 years comes, the same subject is tested again in a very it becomes the same major subject. So I could make comparisons across 3 domains of academic performance, 3 types of tests over 9 years. So, for example, I look at mathematics in 2003, and then 9 years later, 2012. In this, the focus of my analysis is the socioeconomic status, and OECD is conducting the survey, and it is calculated by the parents' education, the parent job, and also different assets in the house. In addition to socioeconomic status, I look at the gender, also how well behaved students are. Then, for example, how much a student is interested in studying, also bullying, and lots of other variables. The object of analysis is students who are 15 years old, and Japan joined this survey from the very beginning. So usually about 6,000 students are taking part in this program. In 2015, there was change to paper, from paper test to computer. And when we usually the test takes time about 2 hours. First, there are 3 subjects, 1 major subject, and then, for example, mathematics, and then 2 remaining minor subjects, science and reading. That is for 40 minutes, and then students also answer the background questionnaire about 30 minutes. So after 2 hours, they are done. The average score is standardized, so it is 500, and standard error is 100. So if you look at the size of effect, it's very easy to visualize. Standard error 100, so that how much the difference we can measure is typical standard error. This is the screen of the test that student facing. This is the question actually that students are expected to read, and then there is multiple choice question on the left side. And then, as I said, in PISA, there is a rotation across major subjects. So, for example, reading was major subject 2000, 2009, 2018, then mathematics 2003, 2012, and then in the next, the current testing. And then also the science was 2006, 2015. So I didn't use 2000, but I look across the major subjects over 9 years. So there was comparison 2009, 2018 for reading, 2003 and 2012 for mathematics, and also 2006, 2015 for science. And I looked how much the effect of social economic status changed over these 3 years. This is the performance kind of descriptive statistics, so you can have idea how well Japan performed. Actually, this is the better slide. This is the performance in the latest 2018. And you can see that Japan is particularly good in mathematics. It became top of the world. And then in science became second, whereas reading is traditionally relatively less successful. This is the results across for reading across time. So you can see that the latest low rank actually is nothing special because it happened also in the past, 2003, 2006. Whereas if you look at the science is consistently very high. And also the same can be said about, not science, but the mathematics is consistently very high. And the same can be said also with about science. Japan rarely goes down to the lower than top five countries. Data set that I'm going to use, as I said, there is a rotation in the major subjects. So, for example, mathematics is 2003, 2012. And then science is 2006, 2015. And then finally, reading 2009, 2018. And the total number of the students answer questions themselves. And also there are questions answered by the school principals about the general atmosphere of learning in the school, not in particular class. So these questions that students answer is about 20, and roughly the same number for school principals, although the numbers could be sometimes relatively low, like, for example, in 2018, with just only 10 variables available. Sample size is roughly 5,000–6,000 students. Questions that are asked at the level of students are shown here. First of all, age, then gender, then bullying, how students is disposed towards cooperation, also social economic status of particular student, and so on. Also study time. These are questions which are answered by school principals. They explain the typical size of class in the school, what is the location of school, whether it's small city, maybe big city, and so on, whether there are some lack of education materials, attitudes of different teachers, and so on. How positive is the participation of teachers in learning process, and etc. This is how the socioeconomic status is calculated. As I said, it combines the profession, also the education level of parents, and also home possessions. And when home possessions are calculated, the students answer questions what they have at their homes, starting from desks or smartphone and so on. There are yes or no question, and there are also questions about how many. For example, for TV sets, there is a question where there are 4 answers: no, 1, 2, or 3 or more, and so on. And then these answers are combined combined into a single index of socioeconomic status. Now I move to the results. Starting from 2003 and ending 2018, this is the results for average prediction residual, root mean squared error, across different algorithms. So here the first is linear orderly squares, then elastic net, and then free machine learning algorithm, random forest, gradient boosting machine, and XGB boost. So, and the algorithm with the smallest prediction error is in yellow. You can see that, first of all, both linear models are completely inflexible as in prediction Y. The typical regression, the prediction error is something like, for example, 2003, 72, 73, whereas machine learning models are roughly 66, really big gap between traditional regression models and very flexible machine learning models. Out of machine learning, random forest shows the smallest residual, but results are actually not so big. And if you do hypothesis testing, how significant are prediction residuals, for example, for random forest and gradient boosting machine, they are not statistically significant. Roughly, they are very similar. Overall, the XGB boost is the best 4 times out of 6. Once is random forest and once is gradient boosting machine. The problem with machine learning is that a model could be very complicated. For example, in the slide that I showed, a typical hyperparameters, it's here. Yeah, the best model included 500 regression trees. Then the number of interaction effects was up to 5. Then subsample is the fraction of data to be subsampled. So if it is 1, then we use the whole data set. But here we're using 75% of the data sampled randomly. And also, call sample rate is the fraction of explanatory variables to be subsampled. So rather than using all explanatory variables, 20 or 30, each regression tree only uses a fraction, a quarter of the original explanatory variables. So in each regression tree out of 500, the composition of regression of explanatory variables is changing every time. So it's very difficult to combine these complicated 500 regression models with lots of interactions and different composition explanatory variables. Of course, no human can imagine that. But fortunately, in machine learning, there are a lot of work to explain these complicated models. It's called explanatory machine learning. And I here report results of 2 such approaches. First one is variable importance plot. Basically, it shows the ranking of variables in their predictive ability. And the second one is partial dependence plot, which shows the expected effect of given variable, while the other variables are fixed at their averages. So let's move to the first one, variable importance plot. And I show you the result for first mathematics when it was a major subject 2003 and 2012. And you can see that here we have ranking. So the most important variable 2003 to explain academic ability in mathematics was the school climate as evaluated by students. Then CS means school level variable as evaluated by principal, and this is the student morale. And so if you go down, then the variable at this seventh place, is actually the variable which I'm interested in, is the socioeconomic status. 9 years later, if we again explain the mathematics, socioeconomic status is no longer 7, but it's at the top. So we can see that it became more important compared over time. What about other subjects? Here I show the result for science. For science, the most important variable was student-teacher ratio, and but socioeconomic status was also about 7, 8. But 9 years later, again, the explanatory ability of social economic status increased, and now it became the third most important variable behind the joy of science, as students, according to students' answers, and also the school climate concerning students. Finally, I show the results for reading. And here we see that initially in the socioeconomic status was not actually in the top 10. It was something like number 14. But in the latest survey, 2018, it was the third most important variable to explain academic scores, academic test scores, after joy of reading, and the evaluation of index of school climate with respect to students at the level of school. So even though the model is complicated, but the relative ranking, we can calculate relative ranking of explanatory variables, and the socioeconomic variable, unfortunately, became even more important. It used to be quite important, but now it's the top 3 most important variables with respect to school student test scores. Next is the partial dependence plots, PDP plots. PDP plots are basically the expectation of average, the expectation of effect from a given variable. For example, here I look at the effect from social economic status on average grade, test grade. We fixed the effect of other variables at the average level, and then calculate average starting from the smallest value, first variable, to the first distinctive value of social economic status. Then next variable. You can see that they are basically very sometimes could be very smooth, but occasionally there are some rapid changes, like in 2012. But overall, there is a positive effect. But it's not linear. Definitely, it's not linear, and the gap between expected effect is getting larger. For example, in 2003, it was between 510 and 540, so something like 30 or 1/3 of standard error, whereas the gap became larger in 2012, between 520 and 560, 555. So the slope of socioeconomic gradient became steeper. Next, I show results for science, and again there is overall very high volatility, but increasing very sharp gradient. Here, the slope of socioeconomic gradient didn't change very much. But if you look, for example, in the final one for reading, then again, it used to be something like between 520, 515, and 530, and much wider in subsequent 9 years later. So if you look at the results of regression model, the regression line can be quite similar to the estimated slope of by machine learning model, but you can see that at the edges, the machine learning often finds the slope is flat, whereas obviously linear model would easily miss this kind of S shape. Okay, so now I move into conclusions. First of all, after applying traditional regression models, OLS and ensemble nets with linear effects, and also machine learning models, we found that the machine learning models have excellent, much superior predictive ability compared with traditional regression models. When we use the try to explain the structure of this machine learning model, particularly the effect from socioeconomic status, then the relative importance of socioeconomic status became consistently higher, unfortunately, over years. And now it's one of the most important variables when we try to explain academic performance. And finally, when we try to calculate the expected effect from socioeconomic status, then again, the slope of the socioeconomic gradient became steeper for most of the subjects. And also we could identify that at the edges, the effect became a little bit smaller. So typical with a kind of S shape, which was important nonlinearity that was missed by traditional linear regression models. I think I was talking for about 45 minutes. Thank you very much for your attention. And this is the slide, the literature. Thank you very much.